everybody. I'm here to talk about some of the memory things in JavaScript. But first of all, a small disclaimer. There will be quite a lot of moving things in my slides, quite a lot of animation. So if this is something that is triggering to you, just be aware of it. But let's start. We know that on a fundamental level, everything we do on the computer eventually gets turned into binary code, essentially just a bunch of zeros and ones, including everything we write in JavaScript. But how exactly does it happen? Through what stages it goes through in between? My talk will try to answer that question and is the result of my own journey down the rabbit hole, trying to understand how variables we create in JavaScript get turned into a bunch of zeros and ones. And I'll try to cover the whole journey, starting from binary code and memory architecture to inner workings of a JavaScript engine like memory allocation and garbage collection. So with that, I invite you on this journey down the rabbit hole with me. Well, I'll show you around. But first, let me introduce myself real quick. My name is Kateryna, as Anjana mentioned. I am Ukrainian, but I live in Tallinn, Estonia right now. I'm a front-end engineer and engineering manager, but I'm also organizer of Tallinn.js, and I brought some of our stickers here from our last meetup. So if you want some, you can feel free to catch me later on the break. But let's start. And let's start from the beginning with those zeros and ones and understand how computers represent and store information. So 0 or 1 is the smallest fraction of information there is. It's like on and off switch, true or false. In early days, computers used literal light bulbs that glowed for 1 and were dark for 0. And it's called 1 bit of information. And with combinations of these bits, we can represent all sorts of data. Small numbers, big numbers, characters, emoji, and even the answer to the ultimate question of life, universe, and everything. There are different types of memory and storage computers use to store these bits in their own unique ways. For example, DVD disks use small indentations on the surface that reflect light differently when being shined on with a laser. And floppy disks, if you remember those, used magnetic encoding, so when the head passed through, it could read that information. But when it comes to the memory that our JavaScript applications use, it is mainly RAM, or random access memory. It's basically a working memory that CPU uses while running applications on the computer. And let's see really quickly how RAM works. First of all, RAM consists with these memory cells, and we can think of them as tiny storage boxes that can hold electrical charge for some time, and we can write to them and read from them. On the hardware level, they are implemented as an electric circuit with combinations of transistor or a combination of transistor and capacitor that can basically hold charge for some time. But of course, the single cell isn't much use on its own. So we can arrange the cells in a grid and then use the address system to specify which cell exactly we need. And you can think of it as like street and house address in real life. So when we take the first part of the address, we can specify the column. And then the second part can specify the row. And then we can read the contents of the memory cell at the intersection. So yay, we just read 1 bit of information. However, 1 bit of information isn't enough in modern computing. We need a way to manipulate more bits simultaneously. So to do that, we can arrange these grids in an array, and then using the same address, we can access multiple memory cells at once. For example, with this 8-bit address that we are using here, we were able to read 1 byte of data at a time. To simplify it a little bit further, we can think of it as a match between the address and data it holds. We can convert address to the decimal format and then represent all available memory as this kind of array of available addresses and their corresponding values. So current RAM that we are using used 8-bit addresses, which means that in total it allows us to store 256 bytes, which is very little in modern computing. But this is an example of memory older computers used, often referred to as 8-bit memory architecture. Modern computers operate on 32 or 64-bit architecture instead, which means that addresses got a lot longer, and therefore they're usually represented in hexadecimal format. But all of the core principles that we just discussed still apply. Now, while we are talking about physical RAM memory, it's important to note that applications, when they run on the computer, they don't interface with physical RAM directly. Instead, operating system maintains this additional layer of abstraction known as virtual memory. And it maps to the physical RAM under the hood, but gives operating system the flexibility to, for example, use the hard drive when physical RAM is running low. And it helps to manage memory usage more efficiently and alleviate some security concerns, but also gives applications the illusion of this large continuous memory space available to them. Now we have this memory, and let's say we want to store something. Let's say it is a variable. More often than not, it won't fit into 1 byte. So then it would occupy a continuous segment of cells in the address space and is often identified as the first address in that space. And it's called a pointer. It means that this address points to the location memory where our data begins. And after that, we can just follow along until we cover the size of our data. In languages like C and C++, you as developer need to manage memory allocation manually. For example, right now you see a piece of code on the screen, it's in C, and it allocates memory for an array of 10 integers. So what we do here, we multiply 10 by the size of type integer to allocate memory needed to store that array. And after we use that array, we need not to forget to explicitly free the memory that was associated with it, so it can be used for other allocations. And you can see it's quite a lot of work and quite a lot of things to remember for you as a developer, but at the same time, it gives a lot of power to optimize memory consumption. Now, if we get to JavaScript, we don't need to do any of that. We can just go around defining arrays left and right without giving a second thought about memory allocation. And it's actually a good thing. JavaScript is a high-level language, which means that it does a lot of things for us, so that we as developers can focus on building features and delivering value to our users. And all of the memory allocation and freeing is done behind the scenes by a JavaScript engine. And what is a JavaScript engine? It's a program that runs within a runtime environment, such as browser or Node.js, that takes the JavaScript code that you wrote, which is essentially just a long piece of text on its own, and runs a lot of transformation on it to turn it into machine code that can be executed by a CPU. There are a lot of different engines out there. For example, V8 that is developed by Google, SpiderMonkey that is used in Firefox and developed by Mozilla, and JavaScript Core, which is part of WebKit and is used in Safari, developed by Apple. And this talk will mainly focus in V8 because it's arguably the most popular of them all, but a lot of the core principles still work the same in other engines as well. So V8 is used in Chrome and other Chromium-based browsers such as Opera and Edge, Node.js and Deno, Electron, and more. V8 itself is written in C++ and is open source. So if you want it, you can go and check out the code for yourself. It's really well documented, and there's a lot of tutorials online on how you can run the developer version of V8 if you wanted to. Now, let's take this piece of code that declares a really simple object and follow it down the rabbit hole to understand how V8 allocates memory for it. So first of all, V8 uses 2 types of memory. There is stack memory and heap. Stack is the region of memory that allocates local context when interpreter goes through your code, basically kind of going through your code line by line and allocating what is needed right now for the execution. And heap is a much larger region of memory that allocates everything that is allocated, that stores everything that is allocated dynamically. Say your objects, functions, arrays, etc. And stack and heap is not something that is unique to V8. These are common ways to structure data, each with their own specific ways of accessing and adding new data into the structure. Now, getting back to our example, first, when interpreter reaches the line with our variable declaration, it needs to allocate memory for the new object on the heap. Since JavaScript is a dynamically typed language, it doesn't know in advance how much space something will occupy in the future. So first of all, it detects how many properties the object has in the beginning, and also it has a lot of internal kind of logic and heuristics to kind of predict how much space something will occupy. So it will kind of dedicate space for it, but then the color property itself will be stored in a different address, whereas the original object will be pointing to it. And it brings to kind of important point that most of the primitive values are actually being stored on the heap, contrary to the popular belief, except for small integers. And then, as our memory is allocated, it can be updated on the stack as well, and our code can be continued to execute. If you run the heap snapshot under the memory tab in Chrome, you can actually see all of this. So for example, here is our object, and you can see all of the properties inside and a lot of other things. Under the hood, V8 uses this superclass called heap object for everything that is allocated on the heap. and contains pointers to all of the internal values for the object itself, plus a lot of useful metadata that V8 uses for optimization. To connect back to what we discussed before, both of these occupy actual space in the virtual memory and, by extension, the physical RAM on your computer. Now, as our program runs, more and more things get allocated on the heap. And if we zoom out a little bit more, we can see that both stack and heap are located on different sides of the memory array dedicated to our application. And as we fill up it with more and more variables, they start growing towards each other into the free space. But of course, it's not like our program is the only thing running on the computer. We need to share memory with other applications. And in the case of the browser, we need to share it with other tabs and browser plugins that you might have open, which might give a little bit more insight why Chrome can be so memory hungry sometimes. Yeah, I love this GIF. Going back from the GIF, let's shift our focus back to the code and explore a little bit more examples of how stuff gets allocated on the heap. From here on out, I'm going to stick only with heap, but stack memory is still there, allocating local context as the code gets executed. So we already know how the object itself is declared. Let's say we declare another variable foo that has the string of the same value, white. And this presents an interesting situation for V8. Because if it was to allocate new memory space for it, it won't be very efficient. We basically would be storing the same thing twice. So instead, V8 uses the technique called string interlining. It detects that both of these are basically the same string, and instead of allocating new memory for it, both of them will be pointing to the same location where the string is stored. And it brings to another important point that most of the variables in JavaScript are just pointers, pointing to locations where something is stored. But what happens if we reassign foo's value? As all of the kind of strings and other primitive values are immutable, we'll allocate new space on the heap for the new string, and then the foo's pointer will be updated so that it points to the new value. I really like analogy from Dan Abramov's Just JavaScript course, where he compares variables to wires that point somewhere. So we can imagine that both color and foo are wires connecting to the same place, and as foo's value changes, wire just changes its end location. Now let's explore another example, a little bit more complicated one. Here we have an object with two properties. And then we create another variable and assign it to the previous one. And then we change that variable's property. And you would see that original object's name property got updated as well. So when we made an update here, it got updated here too. This is something that is called modification by reference and can be really tricky if you are not careful. To understand what actually happens under the hood, let's look at the heap. So as, again, interpreter reaches the line with our object declaration, it allocates memory for the object itself, and this is something that is already familiar to us. It's just that this object has two properties instead. Now, when we create another variable and assign it to the same object, instead of recreating the whole thing, both of these will be pointing to the same location. So that when we update the name property, it would be updated in both, because both of them are basically pointing to the same place. If we zoom out and get back to the mental model that we saw before, this is what happens. And because both of them were pointing to the same place, it got updated in both. To avoid this behavior, we could use something like a spread operator, like this. In that case, if we update the name property, original object will keep its original value. What happens is that the spread operator copies all of the top-level properties, so that when the name is updated, it doesn't impact the original object. Though it still has some limitations. Interestingly, it wouldn't help for all the nested objects out there. So let's say we have a deep nested property here, and we update it for the new created object. It will still get updated in the original object as well. Let's see why that happens. So when we use the spread operator, it copies only top-level properties, often referred to as shallow copying. So that when we update the color property, it will still get updated in both, because both objects' internal code property was pointing to the same location with an object. And as I said, it can be really tricky and can backfire and create some bugs that are really hard to find. So for example, when you're using React and you pass an object as a prop to the component, and you do some modifications with it in the component's code, it actually impacts the object in the parent component and in the parent of the parent component, and maybe going back to your Redux store or whatever else state management solution you're using. And this is exactly why immutability got popular some time ago, because libraries like Immutable.js make sure that all of the references are kind of recreated and not copied. Now we talked a lot about memory allocation, but what about freeing memory that we don't need anymore? So for example, we have the string here, white, that is not used anywhere anymore. And in languages like C and C++ that we explored the example before, you would actually need to free this memory manually. But JavaScript runs a garbage collector for you. In V8, it is called Orinoco, and let's dive a little bit deeper how the garbage collection itself works. But first of all, let's understand how V8 can generally detect whether something is garbage or it's not. So when we have our application, we represent all objects we have as this kind of chain of references that goes from the root. And as our program runs, some of those references stop existing, as we saw in the example above. And it means that they become unreachable from the root, so they cannot be used anymore. And therefore, memory that was associated with them can be freed. If you look at the memory array and just free the memory that was associated with it, it might leave our memory fragmented, which means there's a lot of little gaps and becomes a lot harder to allocate anything new into the memory. So to avoid that, memory needs to be compacted so that we have a long, continuous chunk of fresh, juicy memory available for the new allocations. So if you remember old Windows operating systems, there was this super scary disk defragmenter utility. I remember being scared to use it every time. That did really similar thing to your hard drive. Of course, current operating systems do it automatically for you, and it is not needed anymore, but the process is really similar. Now, let's look at how V8 does garbage collection. So all Heap is split between two main generations, young generation and old generation. Let's look at the young generation first. It's called young because this is where all of the new objects get allocated. It is relatively small, usually between the size of 1 to 8 megabytes. And inside, it is split into two equal parts. And right now, we'll see why. They're called from space and to space. And as our program runs, new objects get allocated into the memory. But at some point, the time comes when we try to allocate something, but there's just not enough space for it. And this is what triggers the garbage collection cycle. So V8 stops the execution cycle completely until the cleanup is finished. First, it needs to understand which objects are still alive, so it traverses through the chain of reference that we talked before and finds the objects that are referenced from there. Then it can copy those objects from space to space, and this is why they're called like that. Now, everything that we had before could be deleted, but of course, before doing that, we need not to forget to update the references that were pointing to those objects that we just moved to a different place. And you can see that this, at the same time, does freeing of the memory, but also compaction, right? Because we now have a long, continuous chunk available in the to space for new allocations. So after that, everything from the from space can be safely removed, and then the spaces can be swapped in place, and garbage collection cycle is finished, and we can continue the execution. So the object that has been waiting can be allocated into the memory, and then our program runs as usual. As I said before, this garbage collection stops the execution cycle completely because it needs to update all of those references, and it cannot be done concurrently. And in earlier versions of V8, you could even see a small lag because garbage collector was doing its job. For example, you're clicking the button and it triggers the garbage collection cycle, and you could see maybe some lag in rendering. Now, V8 does a lot of work in parallel and actually parallelizes this work in up to 7 threads, so it takes only a few milliseconds. And this algorithm is really fast, and it's really simple. It's called scavenger, or sometimes referred to as minor garbage collector. But at the same time, it's really memory hungry because we always need twice as much memory to facilitate the algorithm's work. Remember having to need like from space and to space at the same time, which is okay for small amounts of space, but of course it wouldn't be sustainable for everything. And this is why old generation exists. So V8 follows what is called a generational hypothesis, which means that most objects die young, which is really depressing. But what it means is that most objects get allocated and then almost immediately become unreachable. And if you look at how you write your code, you can actually see those patterns. For example, you have a function that you create a temporary object for, and then you return the value, and this object is not needed anymore, it's not used anywhere. And this is where the garbage collection, like the old generation, comes in. So as our young generation fills up and garbage collection cycle is run, the objects that survive that cycle are marked as intermediate, meaning they already survived one cycle of garbage collection. And then as young generation fills up again, and we run the second cycle, the intermediate objects that survive, instead of staying in the young generation, get promoted into the old generation instead. And old generation is taking most of the heap, and statistically around 20% of the objects survive into the old generation. And this is way bigger, and this is where most of the data is stored. So let's talk a little bit how garbage collection works here. So instead of using the same algorithm that we discussed before, because it's so memory hungry, V8 uses what is called mark, sweep, and compact algorithm. And let's go about it step by step. Let's start with the marking first. So remember that chain of references? V8 goes through chain of references and marks the pointers of the objects that are accessible from the root. Then it means that everything that is not marked is not needed anymore. And so this memory can be used for something else. So this memory can be freed, which brings us to the sweeping part. And the way that free memory is managed is actually really interesting. And let's look a little bit more in detail how it works. So all heap is split into these sections that are called pages. And each page is basically a segment of memory where we can allocate things. And as some of the memory is freed, it leaves some of the gaps that can be available for the new allocations. But if V8 would just go through the whole heap looking for the available space, it wouldn't be really efficient. So instead, it maintains a structure called free list. And it is a dictionary with all of the free memory allocations. And we can think of it as like Airbnb for all of the objects on the heap. So for example, here we have 3 allocations of the size 1 available, and then 3 allocations of the size 2 available. Of course, there is a lot more sizes than that, but this is just an example. Now, when the new object comes and it needs to get allocated, instead of going through the whole heap, V8 just looks into the free list and finds the first available location of the needed size available, and this is where this object can be allocated. Then, of course, this location needs to be removed from the free list because it's not available anymore, and then the execution can be continued. And now, as we talked about the sweeping and how all of the free memory is managed, let's talk about the compaction, and it's also really interesting. So as our program runs, some of those pages become too fragmented to operate. And V8 detects those pages early on and then runs compaction on them. So let's say this page needs compaction, and it works relatively simply, so it just allocates a new page and then copies over all of the occupied values into the new page, so that we have a longer continuous chunk available for the new allocations. Then, of course, after updating all of the references that are pointing to these objects, the old page can be deleted. And now we have the new page with like a big chunk of memory available for the new allocations. In terms of performance, a lot of the work of this algorithm is done out of the main thread. For example, the marking is done concurrently, and sweeping is done concurrently as well. But the compaction bit, again, because it involves updating all of those references, is still done in the main thread. And of course, it is usually not really taking a lot of time, but of course, it depends on the size of your heap. Now we covered both minor garbage collector and major garbage collector, and this is where I would like to wrap up my story. But before that, let's do a little bit of a recap. So the code we write in JavaScript is essentially just a long piece of text. By itself, it doesn't do anything. It needs to be executed inside a runtime environment, such as browser or Node.js. And within that runtime environment, there's a JavaScript engine like V8 that turns your code into machine code that can be executed by CPU. And that engine is using two types of memory: stack for all of the local context while interpreter goes through your code, and heap for all of the stuff that is allocated dynamically. Of course, there's not only allocation, but also memory needs to be freed. So it runs automatic garbage collector. And V8 has two garbage collectors: minor for the young generation, the scavenger, but also the major garbage collector for the rest of the heap. And then, of course, everything that is stored there translated into the virtual memory that is dedicated by operating system for our application. And then that translates to the actual memory cells on the physical RAM that store those zeros and ones. And I aim to cover quite a lot of ground and get overview of the whole journey that our variables that we create go through. But of course, there's a lot more space for you to dig deeper in some of the aspects, which I really encourage you to do because it's really fascinating. And I will share some of the additional materials and resources later in Slack as well. And I hope you enjoyed this journey, and it gave you a little bit more insight of all of the things that happen under the hood when we create variables in JavaScript, and how amazing the tools that we as developers have at our disposal when we are writing our applications. So you can find me on these social media, and I'm super open to any questions, ideas, or feedback you might have, and thank you for the attention.